Thank you, Michael. Hello, everyone. My name is Ashwini, Raina, and today I'm going to talk about our work, efficient compactions between storage tiers with PrismDB. This is joint work with my collaborators from Princeton University and Columbia University. Several new NVMe storage technologies have recently emerged, spanning the cost-performance spectrum. On one side, you have high-performance technologies such as Jianan and Optane SSD that offer ultra-low latencies. And on the other end of the spectrum, we have cheap and dense storage such as QLC NAND that offers low cost per bit, but sacrifices both performance and endurance. Given this trend, we believe that systems built using homogeneous storage can no longer offer the optimal trade-offs between cost and performance. So how can storage systems exploit these trade-offs? We first define the high-level goals of a storage system. An ideal storage system should have low cost, fast reads and writes, and long lifetime. So let's look at these goals one by one. Low cost can be achieved by using tiered storage, by combining NVMe SSD with QLC flash. To achieve fast reads, more reads should be served from the fast tier. For writes, they should go to the fast tier, and if that tier becomes full, the system should free up space quickly by moving data out. And finally, for long lifetime, fewer writes should go to the low endurance tier. Please note in this talk, NVM refers to fast block-based devices and not persistent memory. Okay, so how well do existing storage systems meet these design goals? We look at log-structured merge trees, or LSM, which is a popular data structure used in several key-value stores and databases. Here we show an LSM on tiered storage, upper levels on NVM SSD, and the last level on QLC flash. So this tiered LSM turns out to be 8 times cheaper than a single tier LSM on pure NVM. So it satisfies our first goal, the low-cost goal, but what about performance? Let's see this LSM in action. A put operation writes the object into the memtable, and once the memtable is full, it is flushed to level 0 of the LSM tree. And as more objects are written to make space for newer objects, older objects get compacted down the tree, finally settling down in the last level on slow QLC flash. Now, if a get operation is issued on that object, it ends up reading from the slow QLC tier, and we actually see this behavior in our experiments. In the figure on the right, x-axis shows different LSM levels, and y-axis shows the percentage of get requests served from these levels. What we notice is more than 40% of requests actually get served from the slow flash, which degrades the read throughput. Here we make the observation that LSMs actually have a write-aware data layout by default, and to use NVM to serve more popular data, we need to add some kind of read awareness to it. So we spent the first year of this project just doing that, building a strawman LSM that retains popular objects on NVM. Here we have the same tiered LSM with SSD files. A put operation writes the object into the LSM, which then gets flushed to L0. Let's say this was a popular object shown in red. Once again, new writes will force this down the tree. And as it gets compacted down, we introduce a special cross-tier compaction that we call pinned compaction, that instead of compacting all the objects down, now retains some of the popular objects in the fast tier. In our experiments, we do notice that object pinning helps, and it reduces the access to the slow tier by about 27%, which makes reads faster. But pinning objects results in lesser free space in that level, which ends up triggering more compactions. This ends up delaying new writes and degrades the throughput. And these excessive L3 to L4 compactions end up increasing the write I/O to the flash tier and thus reduce its lifetime. So this led us to conclude that on tiered storage, there exists this fundamental tension between object pinning and compaction efficiency, and that simply retrofitting an LSM on tiered storage is not a good choice for realizing this trade-off. So we designed a new key-value store called PrismDB, whose architectural choices are based upon the following observations. Since NVM has fast random access and high IOPS, We move away from the immutable file format of LSM to mutable, unsorted, object-based layout on NVM. We use a B-tree index in DRAM to index the unsorted NVM objects, and that's okay because the NVM tier stores a small fraction of the database, so the B-tree memory footprint is guaranteed to be small. For object pinning, we introduce a lightweight key popularity tracker and object mapper. And finally, since Flash has good sequential access, PrismDB retains the SSD file layout on Flash. But these architectural changes by themselves aren't enough. The key challenge here is to tackle the compaction problem, which is to migrate objects from this unsorted object-based layout on NVM to a sorted layout on Flash, and in such a way that it achieves all the system goals that we outlined earlier. So to understand the compaction problem better, we show an example here. Let's, just for illustration purposes, we're showing a sorted view of NVM, even though data on NVM is kept in an unsorted way. But this is the view of the B-tree index. This is similar to how the B-tree index would view the objects on NVM. Red here denotes popular objects. Let's say we have two candidate key ranges, R1 and R2. R1 overlaps with 3 SSD files, whereas R2 objects overlap into a single file. So if we were to compact range R1, it would free up 3 NVM slots. And if we were to compact range R2, it does one better and frees up 4 NVM slots. So as you can see, between R1 and R2, R2 seems to be the better choice because it frees more NVM space and causes less write amplification on the Flash tier. So in other words, we arrive at this notion of compaction efficiency, which we call efficient if it frees more NVM space by migrating more cold keys to Flash, and while doing so, it incurs less write I/O on Flash. So we formally model compaction efficiency using MSC, which stands for multi-tiered storage compaction. MSC is our approach to balancing data migration, object pinning, and Flash write I/O. It has two parts to it, benefit and cost. So as we saw earlier, benefit is defined as migrating more cold keys to the Flash tier, and this allows popular objects to stay on NVM, which ends up speeding reads. And if NVM stays free for longer, this also speeds up writes because the NVM tier has more space for the writes, incoming writes. Cost is modeled as total Flash I/O incurred per migrated byte from NVM. And by this formulation, a compaction is considered efficient if it has high benefit and low cost. We design a compaction algorithm based on this insight that computes the MSE metric over NVM key ranges and then selects the range with the highest value for compaction. And what we find in practice is running this algorithm is very CPU intensive. So in the paper, we present an approximate version of this MSE algorithm, which runs much faster. Next, we'll see how well PrismDB performs in the evaluation. Due to the time limit, I'm only going to cover the first two questions. How does PrismDB compare to other baselines? And which workloads does PrismDB benefit? You can find the answers to the other two questions in the paper. OK, so we first compare the storage cost and throughput of PrismDB to 3 LSM baselines. Workload used here is YCSB-A, 50% read and 50% write. X-axis shown here is storage cost, cents per GB, and y-axis is the throughput in kiloops per second. On the x-axis, QLC, TLC, and NVM are single-tier configurations, and multi-tier configurations are shown as het X. X percentage of objects, database objects, sits on NVM, and the rest is on Flash. PrismDB is our system. RocksDB is a popular industry LSM implementation. RocksDB read-aware is the strawman that we built with object pinning. And lastly, Mutant is an academic LSM system that pins popular SSD files instead of objects to the NVM tier. So what we see is PrismDB outperforms both single-tier and multi-tier LSM baselines. And in particular, for the same storage cost. For roughly the same storage cost, PrismDB on tiered storage has 3 times better throughput and 2 times lower latency than RocksDB deployment on pure TLC flash, which is, by the way, the standard way of deploying RocksDB in data centers today. Next, we will evaluate PrismDB on a full range of ICSB workloads. Again, due to time limit, I'll just focus on one baseline, that is RocksDB. X-axis shown here are the ICSB workloads A to F. Y-axis is throughput in kiloops per second. On write-heavy workloads, A, D, and F, we see PrismDB is 2.4 times better than RocksDB. On read-heavy workloads, B and C, PrismDB does 1.6 times higher throughput than RocksDB. And finally, on the scan workload, PrismDB actually underperforms compared to RocksDB. The current implementation of PrismDB does not have a sophisticated prefetcher for scan queries. We turned off RocksDB's prefetcher, and we found that its throughput was similar to PrismDB. Next, we compare the median latency of PrismDB and RocksDB for a write-heavy and a read-heavy workload. X-axis shown here is ICSB workload A and B, and Y-axis is the normalized median latency. Lower, the better. Again, we see compared to RocksDB, PrismDB reduces median latency for reads by 3 times and for writes by 4 times. In the paper, you'll find more evaluations and discussion on PrismDB's limitations. We highly encourage you to take a look at our paper for those details. And in summary, we show that there exists this fundamental tension between object pinning and compaction efficiency on tiered storage. And PrismDB's architecture and multi-tiered storage compaction can actually balance this trade-off. For roughly the same storage cost, PrismDB on tiered storage has higher throughput, lower latency, and is more durable than RocksDB on pure TLC flash. PrismDB is open source. We hope you give it a try. Thank you.